we start now?
Yes, you can.
I was just thinking, I was feeling something when I was teaching online since March, and something stuck in my mind. Now I understand. We all used to present standing, right, rather than sitting. And then I realized, God, we are sitting all the time in front of the display. Anyway, that's another opportunity to do it now. So hello, everybody. I am Alexander Bolotov, working in University of Westminster in London, and I'm going to present our joint work with Alex Saboin, Montserrat Herman, and Pake, colleagues from the University of the Basque Country. So the topic of the talk is the development of the one-pass context-based tableau system for CTL and CTL, branching time logic. The structure of the talk as follows. I will start with motivation, just to give you a few ideas why we're doing it, and I'll try to embed it into the general problem structure we're working on. I'll speak about the branching time logic framework just to refresh that a little bit in your mind. Then I'll give the general idea of the tableau technique, and as we are talking about the development of the one-pass tableau, I'll do more motivation comparing this one-pass approach with the probably more standard two-pass tableau technique. Then I'll concentrate on the nature of our approach, and the nature will be given in the management of so-called context. So we call it context-based tableau. And then I will define the formalisms for the logic we are dealing with, computational logic CTL and extension ECTL. And of course, I will conclude with some remarks. So the first idea of the motivation is to give them general problem structure, which goes probably very well in terms of the standard formal specification and verification approach of the system, where you can either do it using automata emptiness technique or applying the deductive verification. And I'll use just a few techniques such as resolution tableau sequence, and of course there are other deductive techniques that can be applied here. Our specific way, given in this red route, where the deductive verification is supposed to be done by the tableau approach, and more specifically by the one-pass tableau. And you can see this dotted line, hopefully, which connects with the sequence. Why? Because ultimately we aim at the development of a rich framework of so-called certified model checking, where the certification is given by the sequence calculus, and the development of one-pass tableau actually does allow to build the dual sequence, which we aim at when we speak about certified model checking. So just a recap of the branching time framework, we use standard temporal operations such as next time, eventually, in the future, always in the future, until, and I have to say a few words about the models. So the models are such that we speak about infinite paths into the future with the starting point of time, and each path is isomorphic to natural numbers. So to top it up, we have the path quantifiers that allow to form branching time expressions, and I build you a little model here which gives you the satisfiability of these three expressions as an example. The first says that in the state as 0, you satisfy the formula which says that B is true at any path at any point. For all paths, always B. And you can see B labels every state in the model. The green middle formula says that you can find a path in this model where eventually C will happen. And you can see this is the case. And finally, the rightmost formula in brown, I think, tells that you can find a path which is such that eventually you reach the state where D is true, but until that, you don't have C. So not C until D at some path. So just a little model to give you a flavor of the branching time framework and the language of the logics we are dealing with. I think that's familiar to most of you, if not everybody. The tableau construction is building a graph for the tableau using the expansion rules, standardly alpha and beta rules. Alpha would just build the successor state, beta would split nodes into alternatives such as disjunctive rules. Now, more involved are rules for temporal operators that use fixed point characterizations of temporal operations. I give you two of them here that are, for example, on the left, you would see the rule for the formula for all paths, always phi. And because we want phi to be everywhere, we expand the construction by claiming that phi should be null, and wherever you go in the future, you would repeat for all paths always phi. So that recursion is embedded into the fixed point definition. So we use this formula to expand the construction of the top. Now, expanding this constructions, we eventually reach a point where a node is a state. And a state is something which is labeled by either literals or the formula where you know what is happening at the next state, if you want, right? So formula of the type for all pass next or exists pass next. So if you've got only these labels of the nodes, you have a state. And that allows us to propagate the arguments of these expressions, phi itself, to the successor nodes. So I give you an example here, short example, where you can see a label of the node with three next state formulae in the arguments of the path quantifiers. The first is for all paths next time p, and what we want to achieve, we want to propagate p to every successor node. And that means that the flavor of the construction would be that we end up with so-called AND OR tree. And this path that would be generated by this next state construction would be called a bunch, and we will apply dedicated rules to preserve the satisfiability of the formula in this AND successors, if you want. So coming back to motivation, the two-pass Tableaux approach checks the validity of the given formula by creating first a structure, a graph, and checks the eventuality satisfiability on it. That is the second pass. In one pass approach, we just check the validity of the input without the auxiliary constructions. But there's a payoff, of course. We need the mechanism to ensure that that works. And what we do here, we involve the concept of a context, which is formed by the formula that surround the selected eventuality. So before I give you an example, just to recap that in the first logic of our interest CTL computation tree logic, the specifics of the syntax is that every temporal operator should be preceded by a path quantifier. So the first formula is a good CTL formula, exists a path eventually P, and the next one, which expresses fairness, is not, right? So you have the concatenation of box and diamond, which is not the CTL formula. But that would be an extension of CTL, which we tackle as well. So what is the context? The context is the collection of state formulae that are exactly the set of accepted formulae in the language of CTL. And what does context do? It does allow us to force eventualities to be fulfilled as soon as possible. So let me give you a very short example just to illustrate how it works. Say you've got a node which is labeled by these two formulae, just the literal P, and the formula of the type exists a path P until Q. So that's the eventuality, P until Q, and the context of it is that literal P. So let's have a look at the way how the construction of the Tableaux works here. I start with this node that is labeled by my two given formulae. I expand this node and already have a model on the left-hand side where you have, of course, to satisfy P. And because it's eventuality P until Q, I want Q to be true. That would make the until formula true already, right? Alternatively, I'm going ahead to expand the rule using the specific for our construction context-based rule. And you can see what's happening here. I move the context, which is P, as the argument of the until, but with a negation. And that formula on the right, which says that you would have at the next state a path at which at the next state you would have P and not P until Q is the formula that embeds the context in that modified way into the argument of the until operation. So what does it do? You will see now in the few steps. We will now construct a new state. So because the previous one is a state, you can see it's labeled by literal and the constraint exists past next, so it's a state. And then we can apply the next rule, which allows to give the argument of the exists next as a label of the new node. And then you expand this further based on the fixed point characterization. Again, either having a model, which is Q, or terminating the construction because you got the contradiction, P and not P. And that's the way how the this statement that the context forces us to sort of terminate the construction by evaluating, by satisfying initialities as soon as possible works. Little bit more general idea is given on this slide. There is a family of CTL type logics, and I give you the syntax of them here in the slide with a very specific reason. So this covers logic from CTL to CTL star, and you can see there are three in between logics. The logic extended CTL, which allows fairness. Then is the CTL plus, which allows fairness plus Boolean combinations of them, plus ECTL sharp, a logic which we developed years ago because we wanted to manage fairness that is also formulated with the until operation, which we haven't seen before. And then finally CTL star. So these are path formulae of these logics. The state formulae stay the same. And of course, the expressiveness is going up here from CTL to CTL star. So why I'm doing it? Well, simply because, as you can see from this table, we have developed the technique of one pass Tableaux for that logic of ECTL sharp that tackles the until fairness. And that covered already the case of ECTL plus. So what we do here, we're sort of doing a sharp U-turn, speaking in terms of the driving, and coming back to bridge the gap with the logic CTL and ECTL. Why? Because CTL is a good candidate, of course, for the certified model checking. And that was part of motivation for this work as well. So, strictly speaking, we take the Tableaux rules, which are standard for the construction of the Tableaux method. And then all these rules, as you can see, would only be different by preserving the context, which is given here by the capital sigma. So sigma in these rules is a context. We do preserve context, but these rules do not deal with the context itself. The other rule, which I already gave you a hint about, is the next state rule, which generates and or tree. So the idea is that if you've got existential quantifiers, they would dictate that you have the branching, but the branching would have to tackle the paths that are supposed to satisfy this existentially quantified formula. And of course, we propagate the arguments of the for all formula by this next rule, generating and successes in this and or tree. And one of the most important rules in the system manages the context. So that is the rule which I gave you in a very simple way before as an illustration. Now there's the rigorous formulation of the rule. If you've got on the top of the rule the formula with eventuality, Q stands for the path quantifier, could be existential, could be universal, and big sigma is the context. So because it's a minimal fixed point, we split the construction into branches. We either satisfy the right-hand side argument of until, so sigma 2 is true with the maintenance of the context, or alternatively, you preserve the context, you satisfy the left-hand side argument of the until, and you generate the next time formula squeezing the negation of the context with the conjunction of the right-hand of the sigma 1 as the formula part of the until. With some restrictions that makes computation more efficient. The restrictions are that we are removing from the context, doing it all formulae of the type for all always. Why? Because they will be just redundant in the computation. They will be eliminated anyway, so we don't consider them. And that is what we call a context managing rule, the beta plus rule. So top up the set of beta rules. Right, the sort of pseudocode for the algorithm is given here. What we're trying to achieve is to build the Tableaux systematically, expanding using the rules which I described, and we reach the stage when the nodes are labeled by so-called uniform sets of formulae, and these are nothing else but just the labels that are basic CTL modalities, if you want. What it means that they are formulae of the type path quantifier next, path quantifier temporal operation, so basic CTL modality. Now, once we've done it, we are able to apply, to select the eventuality and apply the eventuality rule by managing the context as I described. So that was the overview of the system for the basic logic CTL. Now to tackle the extended CTL, we add two rules, and you can see they deal with the fairness that is the essence of the logic ECTL. So what we have now, take the left-hand side rule. It says that you've got the context sigma, you've got that Q stands for the path quantifier again, you've got the formula that expresses the fairness. So you expand the tablet, generating the successor node, and the rule is based on the standard fixed point definition of this operation and the property of the fairness and the scope of the quantifier. So we did prove the standard soundness and completeness and determination of the procedure. So to conclude, what we have done here, we have extended the method naturally because it existed for linear time logic, and really naturally it's extended to the branching time case, now covering just the gap in this roadmap, if you want. So we have the formulation of the method for CTL logic, for its extension ECTL, and this is much simpler techniques than earlier developed Tableaux techniques for the logic ECTL sharp that tackles fairness with until. Now, what is very important, and this is our ultimate idea, as I said, is to use the constructions to generate the dual sequent calculus, because then we can apply this sequent proofs as certificates for the certified model checking approach. Now, what is important is that the developments that we ended up in this paper are quite intuitive techniques for CTL and ECTL, and they're quite well suited for the automation and amenable for the implementation, which is part of our current and future work. Thank you.
Thank you very much for your presentation. Open for questions.
May I ask?
Yeah, go ahead.
Well, will it work for mu calculus or something like mu calculus?
The one past Tableaux.
Right.
Well, it's a good question. We haven't. I think there is a good reason to say yes, it will, right? But, but I'm not pretty sure how complex and intuitive the developments will be in this case. So that's the thing, because if you come back to this statement that we need to guarantee the soundness and termination of the approach, right? Here we use the context, right? So the context is manageable quite sort of nicely in case of CTL and ECTL, but even in case of ECTL plus and ECTL sharp, what we need to do, we need to expand this concept, and we introduce in those developments what we call an inner and outer context. So there are already complications there, because you would have much complex concatenation of the operations, and that already is a big complication which makes things less intuitive. So what will happen in terms of mu calculus? I expect very similar things, if not worse. But I mean, it's a good question. probably it's a good thing to have a look at.
At least a direction for future work, at least.
Thank you. Yes. Thank you very much.
Thank you.
I'd like to add something there. So I strongly believe that it's not going to work for the mu calculus. So basically what you're doing there is something that Colin Sterling has done 20 years ago. This idea of bringing the context into the formula, and I mean, he called it fixed point strengthening.
Yes.
And so it's actually, I mean, it's very similar to what's been done there under the term focus games, etc. So you see, one question is, would this work for unary CTL? So where you only have finally and generally rather than until and release.
What is unary CTL, by the way? Excuse me.
Yeah, so you instead of until and release, you have finally and generally.
Okay, thank you. Mm-hmm.
I don't have an answer to that question yet. I don't know. Good question.
But you see, then, yes, you know, the mechanism is taken away that you're using here, because what you're doing, I mean, as actually there's a tiny difference here. So in the work that we did there, so Colin and I, so we used the context to strengthen both parts of the until, so the left and the right argument. And essentially what you're saying is that you don't need it on the right argument. But, you know, if I take away the left argument by saying you only have finally and generally, it doesn't work. Yeah. So if you then put the context into a finally in this way, it will become an until. And the problem with the mu calculus is that you may have formulas in which fixed points, it's this so non-A conjunctive fragment. So you may have a formula in which a fixed point variable occurs twice, and it's combined with an and. So that means you then have a fixed point variable in the context of itself. And then, you know, if you want to put that, so that context in to strengthen this fixed point, that just basically has no meaning. Things go just completely berserk then. And this is what makes the mu calculus very difficult.
I agree with that. I have to say that I don't think we are sort of aiming at covering a big sort of bundle of logics doing this approach. For example, extending for more general logic. Like it's a good question to understand whether the method is extendable. And I see a point, Martin, here, right? Mm-hmm. So it well may be the case that it's not even possible, but the whole idea was probably not to cover a lot of logics here, but to cover those that are practically useful in terms of the certified model checking.
Yeah. And I mean, my comment here is,
yes,
let's not worry about the mu calculus.
Exactly.
Yeah, it's a long way there, right?
Yes.
So there is also, so I've done something with a student of mine. I can send you this paper. So we've managed to extend this to some strange fragment.
The time we have,
which is like CTL plus. I mean, basically the fragment is defined in a way like take all the formulas for which it works. And it's not a sort of self-dual, so it's not closed under negation, for instance. Mm-hmm. Because so you can do something like you can have Boolean combinations of until formulas for as long as you don't have Boolean combinations of, I can't remember, but I can send you this paper. Maybe this is sort of a point, or basically that's the end of the road where we went to, or we managed to get to, and we have no idea how to extend it beyond that. Mm-hmm.
Okay,
so I have another question. So this whole thing about one pass and two pass tableaux, I mean, I find this very sort of artificial if you compare what's going on in the world of automata, where it just seems like the right kind of abstraction has been found so that we do not need to talk about one pass and two pass versus two pass systems anymore. And it's just a matter of here's the automaton, here's the algorithm for analyzing it. But anyway, so putting this aside, it always seems like there's general agreement that one pass Tableau would be preferable because it should be more efficient. And I'm wondering, is this really the case? Because if you look, what's happening here is, it seems like a two-pass system would create a small Tableau and then run over it again, whereas a one-pass Tableau would create a bigger one. Because by putting the context in, what can happen is that you have to unfold the fixed points a lot longer. So could it be that actually so this one-pass approach creates a lot larger Tableau?
Right. As far as we understand it now, in terms of the complexity, for example, right, we are not doing better, surely, right, than the two-pass method, and we did compare the way.
Right, so you mean sort of asymptotic complexity, like X time?
Yeah,
of course. Mm-hmm.
Yeah. But in terms of the size of the system, I think on small number of examples, what we saw, just comparing, for example, this technique with the standard method of the two-pass Tableau, we didn't see much difference in terms of the construction for the small examples. So that's sort of negligible in a sense. But when you speak about larger formula, that's quite interesting to have a very, very rigorous approach to compare the two, I guess. So I can take the point that because we expand the expressions and virtually behind it expand the calculation and unwinding of fixed points by enlarging the arguments, right? For until, for example, we would generate sort of different type of the systems, but